and gentlemen. A very warm welcome to the best subscribed online OpenValue meetup ever. Great to see so many of you online tonight. I'm Roy Wasse, your host for tonight. We have subscribers from Germany, Austria, the United Kingdom, the Netherlands, and who knows which other countries as well. Two nice sessions for you lined up. We'll start with an interesting deep dive into the features of the upcoming Java 16. And we have next a premiere of our Java compiler pub quiz. Fun guaranteed, and we will have some prizes after the quiz available. So between the two talks, we will have a small break, and we should finish around 20:45-ish. So now for the first talk. It's about Java 16. It's delivered by someone special. His career started in 1984, and believe it or not, he joined Sun already in 1996. He has been with Java since the very beginning, and he's actively involved in developing Java, doing Java projects, and evangelizing Java. After Sun was acquired by Oracle, he stayed there for a number of years, and now he's Deputy CTO at Azul. I'm talking about a true Java champion, 2 times Java rockstar, veteran developer, seasoned speaker, and all-round friendly guy, Simon Ritter. Welcome, Simon. Great that you're in our show tonight.
Thank you very much. Great, yes. So the idea behind the presentation this evening is to talk about what's coming in JDK 16. And normally I do these presentations after the release of JDK whatever, but this time I've decided to do one in advance. So you actually get to know what's coming in, what is it, about 6-7 weeks now from when it's going to be released. So let's talk about JDK 16. So the first thing is that this is now, can you believe it, the 7th release under the new-ish 6-month release cycle. And so we've been doing this for sort of 3.5 years now, and we've seen that this seems to work really well. The idea of having a release of Java every 6 months, one in March, one in September, has changed the way that we're able to add things to Java. And not just in terms of being able to do things more quickly, but as we'll see as we go through, the idea of these incubator modules and preview features. This is a big change in terms of how Java is developed. Rather than having to wait years between releases and therefore not being able to include preview features and incubator modules, now we can do that because we can make changes in the space of 6 months and then decide, yep, okay, we've finished something and we can add that to the core platform. So if we look at what we've got in JDK 16, there are 17 of what are called JDK enhancement proposals. And that's really kind of like a big chunk of work that's a new feature that's being included that affects pretty much any part of the JDK. It could be tooling, it could be the language, it could be the class libraries or the JVM itself. 3 of those are incubator modules, which means they're new APIs that aren't being made part of the standard right now. Give people a chance to have feedback on it, show whether the feature is right. Potentially you could even remove it if we wanted to. And then we've got one preview feature which applies more to things around the language or the APIs that are part of the Java SE standard. Looking at the Java SE standard, there are 58 new core class elements. And I actually went through this morning and worked out what all of those were. There's 1 new class, there are 3 interfaces, 2 constructors, 45 methods, and 7 fields. And that actually affects quite a wide range of different things. Some of them we'll kind of cover a little bit later on. There's actually, I found there was about 2 or 3 new methods in the Swing API, which is nice to see that that's still getting some attention. Okay, if we look at the JEPs that we've got, there's a few that we can kind of get through fairly quickly because they're not really things that will affect us as developers. So some of those are to do with the build and infrastructure of the JDK itself. First of those was the ability now for C++ 14 language features to be used. Now, obviously, you immediately think about, well, hang on, this is Java. Why are we using C++? But of course, the JVM, much of the JVM is written in C++. So what they've decided is to move from the older version of C++. They weren't even using C++ 12. They were using C++ 98-003 as their standard for the environment that they are developing the JVM in. And so they've now decided to bring that up to date with C++ 14, which I guess is only, 7 years old, although that probably is the most modern one. So that's now enabling people to use more features in terms of the development of the core platform. A couple of things in terms of how the source code for JDK is hosted. It used to be on Mercurial on java.net, and now they've moved that away. They've moved everything over to Git and then hosted it on GitHub. Clearly, this is a great idea because, pretty much everybody uses GitHub for project hosting, and, being able to do pull requests and things like that just makes life a whole lot easier. A couple of things in terms of specific ports for the JDK. There's two new ones now. One of those is the Alpine Linux port, specifically around using the Muscle C library. And that's really targeted at things where you're using microservices and you want the smallest possible image for your Docker container. So you can use Alpine Linux, get a nice small image for your Linux part, use JLink, build your runtime specifically for your application, and get that minimal footprint. The other thing that's happened is the Windows ARM64 port. And interesting thing here, you see, because this is actually contributed by Microsoft. I never thought I'd kind of say that, but there you go. Microsoft have contributed to the JDK. Now, I need to be very fair to Microsoft here. Microsoft have changed a lot over the years, and they've become very open to, open source, but also to Java as well. And we've seen that they, sort of probably beginning of last year, maybe even the year before, they acquired the JClarity team led by Martin Verberg, who's the leader of the London Java community as well, very well known in the community. And so he now works for Microsoft and is sort of leading some of their Java efforts. So they've got some very skilled people working on that. So it's good to see that they're contributing to this as well. Right, so now let's look at specific changes in JDK 16, and we'll start with the ones that are focused on the language itself, and then we'll look at libraries, and then we'll look at the other things. So the first of these is something that's already been introduced in the JDK, but it's been modified a little bit, and it's now being made a full part of the Java platform. And this is to do with the use of instance of. If we look at a simple piece of code that we might use in Java, well, let's go back to Java 8. So what we would do is we'd have an object which we don't know the type of specifically. And what we need to do is to test that to see if it is a specific type and then use it as that type. Now, in order to do that, we can do something like this, where we use instance of to say, is our obj an instance of string? If it is, then we have to explicitly cast it to a variable of type string. So we get string s equals explicit cast string obj. That all works fine, but of course it's a little bit more verbose than we want because we actually have to create a new variable and we have to do that explicit cast. Now, the new feature, which is now part of the Java language, so it used to be a preview feature, now in JDK 16 it is a proper feature in Java, it's now in the language specification, is the idea of pattern matching for instance of. And we can extend the code that we had before a little bit, make a very small change, but make it much easier. So now we do if obj instance of string, and then we specify a variable name, so string s. And that way, if our object is an instance of string, it gets assigned to s automatically, and then we can use that in the body of our if statement. But clearly, we can only use it in the true branch because that's where it is a string. If that test fails, it wouldn't make any sense to be able to use s, and the scope of s doesn't extend to the else branch because it's not a string. So we wouldn't want to be able to call methods on it. We can take that a little bit further. And so what we can do is we can say something like this, where we test obj instance of string s, and then we do and s.length is greater than 0. Now, because we're using the and operator, we know that the left-hand side of the operator has to be evaluated first, and only if that evaluates to true do we evaluate the right-hand side, because clearly it's an and. So if it's not a string, then we never call the right-hand side of the operator. We never bother to try and call length on something which isn't a string. So that will work. Everything is fine. That will compile, and we can run our code. However, if we would try and use the or operator, that wouldn't work, because remember, if it's an or operator, then we have to evaluate both sides. And clearly, if obj is not a string, then we won't get s assigned to it, and therefore trying to call the length method on s would be a compiler, wouldn't fail, and so it gives us a compiler error. So we get a slightly better way of using this kind of thing. Now, the way that the scoping of these variables work is what they call flow scoping. And you can end up with some quite interesting aspects of that. So again, what we can do here is we can say if not O instance of string S, so if it isn't a string, then we'll return from our method, which means that after that, string S is still valid. So the scope, it is in scope, and that way we can then call s.length on that and print it out quite happily. So even though it's in the if statement, because we're returning from that, because it isn't a string, we can then use s afterwards, and the scope is perfectly valid. However, you do need to be careful of this scope, because sometimes you can get scope that hides what you would expect. In this class, what I've done is I've created an instance field called string s and assigned the string 1 to it. Then I've created a method called testMyObject, pass in an object, use the pattern matching, do if O instance of string s, then within that true branch, I can use s, the scope of it is the pattern variable, which is essentially O. I can print out what that is, which will be the contents of O, and then I could modify it. Now, this is one of the changes that's happened between the version in JDK 15 and JDK 16, which is in JDK 15, the pattern variables were implicitly final, but now they've decided to change that so you can change the value of it. So we could do s equals s plus 2. However, once we come out of that if statement and we print out what s is, the scope of s in terms of the pattern variable has stopped. So now we're back to the string s, which is the one that we have as our field in the class, and so we would print out 1. So you do need to be a little bit careful about that. That's one of those things that you could have some interesting bugs that might appear with that. A couple of things that changed, as I said. First of those is that the feature is now final. That means it is part of the Java SE specification. 2 minor changes that were made. First of all, I already said that the pattern variables are no longer implicitly final, meaning you can change them if you want to. And they also introduced the idea that it's a compile time error if you compare an expression of type S against a pattern of type T, where S is a subtype of T. So you need to think about that a little bit carefully. But here's an example. You say, if you say if X instance of obj O, well, that's always going to be true. So it doesn't make any sense to do that because it's pointless. So don't do that. It will give you a compiler error. And that's just one small change. So as I say, this is now a full feature in Java, part of the core language. Next thing is, again, another feature which was introduced back in JDK 15. Yes, JDK 15 as a preview feature, and now is going to be a full feature of the language again. And this refers to or relates to Java inheritance. Now, we know Java is an object-oriented programming language, and so we have all these things like inheritance. So we can do something like this. We can have a shape class, and that can have 3 subclasses: triangle, square, and pentagon. The thing is that we don't have any control over which classes can subclass another class, except for the ability to mark it as final. So if we mark it as final, we're saying nobody can inherit from it. Nobody can subclass it. But that's the only control that we have. What we introduced in JDK 15 as a preview feature, and now as a full feature in JDK 16, was the idea of sealed classes. So sealed classes, as I said, not part of the Java SE standard. And in order to use this, you have to specify both on the compiler flags and on the runtime flags that you want to use this feature. So you have to do enable preview, and specifically for the compiling part, you also have to specify which release you're using the preview features of. So this is actually now in the second preview. It's not actually a final part yet, but it's a second preview. And what it allows us to do is to provide control over which classes can subclass another class. And as I've said here, you can think of final as being the ultimate sealed class. One interesting thing about this was when I looked at this, I thought, that's kind of interesting because it also applies to interfaces. So isn't sealed classes the wrong name for this? I thought it should be called sealed types. And I posted a tweet on this, and Brian Gertz came back and he said, well, no, it used to be called sealed types, but then they decided they call it sealed classes because technically an interface is also a class in the technical sense. So it was kind of an interesting learning experience for me on that one. So sealed classes, one of the things they use is, and this is a slight change in terms of JDK 16 over JDK 15, they now have the idea of what are called contextual keywords. In the past, they had the idea of restricted identifiers and restricted keywords because they wanted to add new keywords to be used in certain places in the syntax of the Java language, things like sealed, permits, and non-sealed. And in the past, the way they did that was by using restricted identifiers, sealed and permits. You could still use them as variable names, but they were valid in terms of keywords only in certain places. So that's the idea behind that. So there's essentially 3 new keywords that you can use in the Java language: sealed, permits, and non-sealed. One of the restrictions of sealed classes is that if you are going to use them, then all the classes that take part in that must be in either the same package or the same module, so that there's visibility of these different classes between the parts of the system. So how this works is now you can say public, and in the case of our shape, you can say sealed class shape. And then after that, you can specify which other classes are allowed to subclass shape by using the permits part of this. And you can say permits triangle, square, and pentagon. And that way we're restricting the classes which can inherit from shape to only those 3. If we then try to compile another class called circle and we said it extended shape, then we get a compiler error because it's not permitted in the definition of the shape class. Now, when we specify subclasses of a sealed class, we have to explicitly state the inheritance capabilities of each of those classes. And that can happen in one of 3 different ways. So if we look at the example we had before of our shape, what we could do is we could extend the ceiling of that class. We can say, in the case of triangle, public sealed class triangle, and then we can permit some other classes to subclass it. So we could permit equilateral and isosceles to extend that. What we could also do is we could say, in the case of square, that we don't want anybody to extend that any further. So we can use the final modifier and we can say final class square extends shape. And then the third option we have is to unseal the class. So in the case of the pentagon, what we're now going to do is we're going to say public non-sealed class pentagon extends shape, meaning that now anybody has the ability to extend the pentagon class. So you can either extend the ceiling of the class, you can stop anybody from extending it, or you can allow anybody to extend it. So there's 3 different possibilities there, but you have to specify one of those for each of the classes that extends a sealed class. There's no default. Next thing, simple Java data classes. Again, this relates to another preview feature, which now is a full feature in JDK 16. If we look at something like this, class point, essentially it's a tuple, and we've got 2 values, x and y. Now, in order to do that in Java, we create a class called point. We specify 2 fields for that, final double x, final double y, and then we have a constructor where we pass in 2 doubles, we assign those to our fields, and then we have 2 accessor methods, which we'll call x and y, which return x and y. That's fine, except we've got 14 lines of code for a tuple. And that's just, it's way too much boilerplate code for what we really want to do. There should be a simpler way of doing this. And now there is. So records, as I said, we're introducing JDK 14 as a preview feature. They've been through a couple of iterations in terms of making some minor changes to it. And now they are a final part of the standard. They're in the Java SE specification, part of the language. One of the things that they changed in JDK 15 was they made record fields truly final. This is the first time we've actually had truly final fields in Java. In the past, even though you mark something as final, it was still possible to change it through reflection. Now, even if you try and change the field of a record through reflection, you'll get an exception thrown for illegal access. They've also made some restrictions. Again, JDK 15, they removed the ability to include native methods in records. And that's because they felt that could introduce behavior that was dependent on some external state. Didn't like that idea, so they got around that. And then they've also, in JDK 16, made a change, which is not actually specifically to records, but it allows records to work in a better way in the Java language. So they've said that inner classes can now declare either explicit or implicit static members. So now an inner class can declare a member that is a record class. So how does this work? Well, very simple. If we look at our point that we had before, rather than having all those 14 lines of code and having explicit constructors and accessor methods, all we do is we create a record called point, and we use the same sort of syntax as the constructor. We say which variables are going to be held within this class, the record, and in this case, it's $x, $y. The body of the record has nothing in it because we don't need to do anything extra, and that will essentially provide everything that we had in our class before. We also have a little bit more flexibility, so that we could have a situation where we've got a record that's called range, and it has a low and a high value. But in this case, we want to do a little bit of extra work in the constructor. And to do that, they've introduced the idea of a compact constructor. So as you can see here, we can define a constructor, but we don't have to specify the parameters that are passed to it because we've already done that in terms of the record definition. We know it's going to be low and high. Within the body of that constructor, the compact constructor, we can then do some testing. We can say if low greater than high, we can throw a new illegal argument exception and reject that because it doesn't match what we're trying to do with our record. So it gives us greater flexibility over how we define our record. Now, there's a few extra things that you need to know about records. First is that the compact constructor can only throw an unchecked exception. So we threw an illegal argument exception, which is unchecked. We can't throw a checked exception. There's no syntax with the compact constructor to say that it throws a specific exception, checked one. So we can only throw an unchecked exception. It's a little bit of a limitation. There was quite a lot of discussion about this in the mailing list, but at the end they decided just to go with the idea of unchecked exceptions. Because the record is an object, as all classes are, then you can actually override 3 of the standard methods. So you can override the equals method, the hash code, or the toString method. That will work fine if you want to provide your own implementations of those. The base class of all records is java.lang.record. Now what that means is that record cannot subclass any other class because it already subclasses record. And we only have single inheritance of types in, well, single inheritance of state, I should say, in Java. What we can do is, if we wanted to, we can actually implement interfaces in a record. Records also do not follow the Java bean pattern. And this was another one of those things that there was quite a lot of discussion about. So rather than the accessor methods using get to say which field you want to reference, so get X or get Y, they use the shorter X and Y. Personally, I don't know, I prefer get X and get Y, but you know, it's one of those things, you know, do you prefer tabs or spaces? Do you prefer VI or Emacs? Instant fields cannot be added to a record. If you specify a record that takes 2 values, X and Y, you can't then have another instance field called Z unless it's static. So you can have static fields in your class, but you can't have instance fields added that aren't in the definition of the record. And records can be generic. So, you know, as you would expect, because they are very much like an extension of class. You can think of records in the same way that enumerations are. So enumerations are a special kind of class. records are a special kind of class. In JDK 15, the way that records worked was extended so that you can now use local records. It's like a local class, and it is implicitly static. And we can do something like this. So we've created a method called find top sellers. And what that's going to do is it's going to take a list of people who are selling things for us. And what we're interested in is a list of the people who, or list of sellers ordered by how much they sold in a particular month. Now, to do that, we'll create a local record, which is a tuple that contains a seller and how much they sold in that particular month. Then what we can do is we can use our sellers as a list, take a stream from that. We can map from the seller itself into our new record, putting the seller in and then retrieving the amount they sold in a particular month. Pass that into our sorted method and sort based on comparing who sold more than other people. Map that back from the sales record into the seller for that particular record, and then collect it into a list. So you get an ordered list of the sellers for that particular month based on how much they sold. And as you can see, it avoids extra work in terms of our stream processing by using a record to do that. Records will work with sealed classes. So we introduced those in JDK 15. Now they work with records as well. So what we can do specifically with interfaces, because we can't extend a record as another class, but what we can do is use interfaces. So we can say we've got a sealed interface called car, and that permits red car and blue car to implement that. So we can say in the case of record red car, even though we can't extend another class, we can implement the car interface, and similarly blue car can implement car as well. So we've allowed those, we've permitted them to be implemented by those records, and we can do that so it all works nicely together. Library changes. So that was all the language changes. I don't know if anybody's got any questions, just because I know we were saying that we'd see if people have.
So there are a few questions actually, Simon. So let me relay them. So the first one was kind of already answered, but let's just double check if we got it right. So about JEP 394. So you had an example with a loop, and maybe you can show the slide. I don't know if that's a convenient view. If you would do print outside of the if block, what? Yeah, it's all the way back.
Where is it?
Yeah. So what if you would print outside of the if block? What would be printed? 1, 2?
No, you see, that's the point. So when we modify S within the if statement, we're modifying the pattern variable. So that's actually modifying what was passed as O. So if we pass in the instance field by using the same name for the pattern variable, it's just one of those situations that I mean, it happens in other places in Java as well occasionally, but it's just something to be aware of.
Okay, thank you. So a question about sealed classes. Okay. Can sealed classes be overridden by reflection, for instance, with Mockito?
Good question. No, because the whole idea is that it is sealed. So yeah, I'm fairly, I would have to double check that, but I'm fairly certain that wouldn't work. I'm fairly certain, but I will have to double check that.
Would be interesting. Yeah, so then about the use cases of a sealed class, Wouter already suggested in the chat that it plays nicely together with pattern matching. We also mentioned an example with records. What would you say are more typical use cases for sealed class?
I think it's just around the idea of being able to have a cleaner design. So you can say, okay, we're going to have these particular classes, we'll restrict where those classes can be extended, and it just gives you more control over your design, so that if somebody comes along and goes, oh, I can see that class over there, I'm going to extend that, I'll use that, because then if you make a change to it and the person who's used that doesn't know about that, then obviously you can get a problem because behavior changes and the person who's using it isn't aware of that. Whereas if you have control over it and you say, okay, only triangle, square, and pentagon are going to be able to use this, then when you make a change to shape, you know what impact it's going to have on the classes that you've allowed to or permitted to extend that. So I think that's probably the real benefit from that.
Clear. So a question about records. How to get setter methods in records?
Yeah, no. So the whole point about records is they're immutable. So there is no idea of a set in there. So you create a record and you set the values, it's immutable, and that's it. So that there is no set associated with it. If you want to have set, then you have to create your own class. Again, it was something that was discussed, but the idea for records was that they are immutable.
Okay, so one question coming in right now from Nick. Will there be any sealed classes in the JDK itself?
Oh, I would expect there will be lots of sealed classes in the JDK. Yes, very much so. In fact, I would say that we're probably looking at a large part of the JDK where people, I mean, yes, I think that there could be a lot of places. Lots of places, but not all of it.
Okay, thank you. Those were the questions for now.
Okay, cool. Right, so library changes. So the first thing is adding Unix domain socket channels. It's one of those things that you kind of look at and go, how is it taking that long to add this? But apparently this is one of those things that's just kind of slipped through the net until now. So what they've done is they've added the ability to create a socket channel which uses the Unix-based way of doing sockets. Typically, this is used for inter-process communication on the same machine. If you didn't use a Unix-based socket channel, the way of doing it as an alternative is using a TCP/IP loopback connection, but this provides identical behavior, but it's much better in terms of security and performance. So you don't have all the overheads of having the TCP/IP stack involved. It just goes straight through the operating system through a file, and you can do it something as simple as this. You just say var Unix domain socket address of /dem/foo. Use a file as an endpoint, and that will work quite happily. Don't use a constructor, use factory methods for that. Streams map multi. So this is an interesting thing because this has been included in JDK 16. And we seem to get these little changes to the Streams API once in a while. And so this is quite interesting. When I looked at flat multi, when I looked at map multi first, one of the things that describes it as being similar to flat map. And I looked at the description and I thought to myself, what's the difference between this and flat map? Because essentially the description is that each element on the input stream is mapped to 0 or more elements on the output stream. So that's exactly what flat map does. But the difference is that, as the name would imply, you can actually do a mapping at the same time. And the way you do that is through a by consumer. By consumer is one of the interfaces that's part of Streams already. So to give you an example, what you can do is you can do a 1 to either 0 or 1 mapping. In this case, what I've done is I've taken a stream of words, languages that we use to program with, and you can pass that into map multi, and then the by consumer we define through a lambda expression. By consumer takes 2 arguments. The first of those is essentially the element that's coming from the stream, and the second is the consumer that's going to be used to do something with that. And then the implementation of that by consumer, the body of that will test the length of the string. And if it's greater than 4, what we'll do is we'll take the consumer that we've got and we'll call accept on that and pass the length of the string. And essentially that's then what gets passed to the output stream. So any strings that are longer than 4 will see the value of the length of that string as a result. So when we run that and we use the for each to just print out what is on the output stream, we'll see 6 followed by 10, because what we're seeing is Python followed by JavaScript, because they're the only words that are longer than 4 letters. So that's equivalent to using basically a filter and then a flat map. Yeah. You can also do a one-to-one example. And I looked at this and then I thought, well, that's interesting, but it's actually really pointless. And the reason I say that is because what you can do here is you can, again, take our stream of strings, then you can do map multi, where we take our by consumer, the string of strings, and our consumer, and then all we're going to do is simply call accept on the consumer for every element on the input string, or input stream, and simply return the length. That's exactly the same as just doing a map. So I wouldn't bother doing this. There's absolutely no point in doing that, but I just included that to show you how it could be used. The place where it actually becomes more useful is when you want to do a one-to-many type of thing. So here what we're doing is we're saying, okay, take the words on the input stream and use our map multi, but this time what we want to do is to output the length of each word, the number of times that it has letters in that word. So we're going to return four times, we're going to return six times, and so on. Now to do that, again, we use our map multi. We have the by consumer, which has the strings from the input stream and our consumer. Now the interesting thing here is that we can call the accept method on the consumer as many times as we like. So all we do is we create a loop and we say for I equals 0, I less than the length, I plus plus, and then call accept that number of times on the consumer and pass in the length of that. So we'll see those numbers come out. So we can see how that works. So this allows us to do quite complicated things without needing to do quite as much complicated code. Now, one of the things is the implementation of this. So in terms of the default implementation, as I understand it, this essentially uses the flat map to do this. And so underneath, what's happening is it's using flat map to essentially do everything for us. But this could be improved a lot, because the way that this works means that rather than the way flat map works, where we create a new stream of output for each of the things on the input, what we could do is actually eliminate the need for creating a new stream each time, and then just make it a little bit more efficient that way. Vector API. This is one of those incubator modules, so it's not part of the Java SE specification yet, and you need to turn on the use of this. And what this is designed to do is to enable certain computations to be done in a more efficient way on the hardware that you've got available, and specifically around vector computations. So vector computations are where the processor you've got has very wide registers available. And this has been around for quite a long time. Intel introduced it, I think, with the SSE, some of the SSE instructions, probably on the Pentium, way back when. More modern hardware uses what's called AVX, AVX2, and AVX512. And the registers that you have available, as I say, are wide. So on AVX, it's 128 bits. AVX2 is 256 bits. And you'd be surprised to know that AVX512 has 512-bit register. So what you want to be able to do for certain operations is, if you're processing arrays of elements, rather than doing them individually with one instruction for each element, you load up your very wide register with a number of these elements in one go, and then apply one operation to the whole register in one clock cycle. So it's essentially single instruction, multiple data. Been around for a long time, nothing terribly new. Problem is that for some things, it's hard for the compiler, the JIT compiler in the JVM, to identify when these things can be used. Ideally, we wouldn't need to do this. Ideally, the compiler would identify everything for us, and we wouldn't need to do this. But there are situations where it's actually better to use an API to do this. So here's an example. Simple scalar computation where we've got 3 float arrays, and what we want to do is we want to iterate over the array A and array B. We'll assume they're the same length, and we're going to calculate a value for the float array C by doing a squared plus b squared times -1. Now, as I say, if a compiler is good, and Azul have been doing a lot of work on our JIT compiler called Falcon based on LLVM, I would expect our compiler to recognize this as a vector operation anyway. But with the older C2 JIT compiler, it doesn't recognize it as something that can use vector operations. What we can do then is we can actually set this up so that it will use vector operations if they're available. To do that, the code is a little bit more complicated, it has to be said. So what we have here is, first of all, we have to set up a species. A species defines what the vector operation is that we're trying to use. So in this case, it's a 256-bit wide register. So hopefully you're running on AVX2 or AVX512 hardware. And then in terms of what we do with our code, it's very similar to what we've had before. So we take our loop, but this time, the first thing we need to do is create a mask. So we're using our species as a mask to say, okay, we're going to be using this register and we need to fill elements into that. And then we create a float vector from the array using that species, using the input from the floating array A, using our index I, and using the mask to indicate where these should go. Same thing for our array B. And then we calculate the result of the value C using the two float vectors that we've got. So we do mul, add, mul, and negate. I've got to say, one of the things I look at this immediately and I go, why not just use multiply and negate? Why do we have to shorten these things? But anyway, bit of a bugbear of mine, but that's what they've decided to do. So we've got mul and add and neg. For a memory access API, again, this was something that's going through a development process in terms of being an incubator module, and this is now on its third incubator iteration. And this is part of Project Panama, which is designed to replace JNI, so that if we want to access either native memory or native methods, native functions, then we can do that in a much simpler way. So the foreign memory access API is sort of related to Panama, but also is partly related to replacing things like sunmisc unsafe, so that we don't have to use an internal API. Idea is safe and efficient access of memory outside of the Java heap. In the same way you would with C and C++ using pointers. We don't have explicit pointers in Java, so this gives us a way of doing that. Essentially, there's three parts to this: memory segment, which models a contiguous area of memory; a memory address, which models a memory address on or off heap; and a memory layout, which is a way of programmatically describing a memory segment. How does that work? Well, we can do something as simple as this, where we can create a memory segment. And what this does is it allows us to, in this case, we're allocating native, which will create a native memory buffer of size 100 bytes. And then we use our loop to put 25 integers into that area of memory. So we can set int at offset from our memory access, use the segment that we've created, and then we have to calculate the address, the offset, manually, understanding that each of these things is going to be 4 bytes in width, and so we have to use a stride of 4 so that we get the right position. Now, obviously, that's a little bit less than ideal because we have to understand the size of the objects, and we need to be quite careful about that. So there is another way of doing this where we can use the memory layout and a var handle, which gives us simpler access to structured data. Now, in this example, it's probably not a very good example because we're just using integers, but one of the things you can do with memory layouts and sequence layouts is effectively define a struct that you would have in C. So you can have quite a complicated layout of your data. But in this example, what I'm just doing is I'm saying, okay, let's use the same idea that we had before. So we want 25 ints that we're going to put into our memory. In this case, what we do is we create a memory layout with a sequence of 25 somethings, and the memory layout that we're going to put in there has 32 bits in it. I'm kind of intrigued. I haven't tried this yet, but I wonder if you can use number of bits, which is quite sort of unusual. I mean, could you use 36 bits? Could you use, I don't know, 17 bits? Probably not, but I do need to try that at some point. And then you can also specify the byte ordering. So if you call native order, that will use whatever's the underlying architecture of your hardware, or you can specifically set it to being big endian or little endian, depending on what you want to do with that. Having created your sequence layout, what you then do is you use create a var handle So you take your layout, call var handle on that, and then in order to determine what's that going to look like, first thing you have to pass in is the class that represents the object or the type that you're actually going to use with that, which is a little bit interesting here because we use int.class. Even though int is a primitive, it's not a type in the sense of a class that we normally have. There are special classes represented within the JVM that we can call if we need to refer to an int as a class. We'll kind of come back to that in a minute because we'll talk a little bit more about Valhalla. So we can do that, and then we can use a path element to indicate the sequence that we're going to use for this. And then in terms of being able to use that, we put our memory segment inside a try with resources block so that when we've finished with this, we can then reclaim that and we can have it garbage collected so that that can go away. And in this case, we'll go through our elements that we want to put in there. And this time we don't have to calculate the offset manually. We can just say index element handle set in the segment the value that we want at the position that we want. Linked to that, if you excuse the pun, is the foreign linker API. And this is a new thing in JDK 16 that's about making it easier to access libraries, native libraries, rather than using JNI. And as if you've ever used JNI, there's quite a lot of work that you have to do in terms of generating header files. You have to generate C code, you have to generate Java wrappers, all sorts of stuff like that. And it gets quite involved. With the foreign linker API, part of Project Panama, what it's designed to do is make that much, much simpler. And unfortunately, they haven't put the JExtract command into the JDK yet. Hopefully, before this becomes a full API, they will include that as well, because that makes things even simpler. And a lot of the code that we see down here just goes away. But the way that this works now is if we wanted to use a function from outside of the JDK on the operating system, let's say we want to use the getPid function, then what we can do is we need to get reference to the linker that's available through the JVM. Then we need the library lookup. And what that, in this case, we're doing is we're saying, give me the library lookup for all of the methods and functions that we have available through the JVM. Then using that, we say, okay, create the link or use the linker and create a down call handle. There's also up call handles, which are a little bit more complicated. Create a down call handle using the lookup to look up the getPid function and then get the reference to it. Then we tell it what type the method is. So it's an int. Again, we use int.class, and then the function descriptor. So it's a C linker with a C int. So we're mapping the C int to the int in Java. And then we can simply say print getPid.invokeExact, and that will return the process ID of the JVM that we're running. As I say, the code is quite complicated in this case. When you get to use JExtract, a lot of this shrinks down because you basically run JExtract first, saying these are the functions I want to be able to use, and a lot of the hard work is done for you, so you can just make a single method call and off you go. Warnings for value-based classes. So this is part of Project Valhalla, and Project Valhalla has been around for a while. It's quite a big change that's proposed to the Java platform and essentially adding value types to Java. So what we would do, one of the parts of Valhalla is to introduce the concept of primitive classes so that we can have a collection that's not using the wrapper classes, it's using the primitive. So you could have a list of type int rather than a list of type integer. So in order for that to work, what they've said is that the primitive wrapper classes are now designated value-based. And part of what they need to do for that is to eliminate the idea of constructors. So the constructors of the wrapper classes were deprecated in JDK 9, and now they're actually marked for removal. The reason for that is that what they don't want you to do is to call the constructor so that you essentially end up with, let's say you call integer with a value of 3, and then somewhere else in your code you call a constructor integer with a value of 3. You would get two different instances of the object. What you don't want with value types is to have that. So what you really want is to call the factory method, which gives you the integer with 3 in it. But then when you call the same factory method in a different part of your code, rather than getting back a different instance of integer, you get back the same one, because an integer with 3 in it is still an integer with 3 in it. Anyway, so that's what all that is part of. And then also, if you attempt to synchronize on an instance of a value-based class, that will issue a warning. So it's the same, trying to get around that problem. A couple of things, other changes, just to wrap up. Elastic metaspaces. This is essentially making the use of memory within the JVM more efficient. So this is what used to be the permanent generation class metadata, which is used by the JVM itself. When classes are unloaded or they're no longer required, then that memory can be returned to the operating system more promptly, so it reduces the overall footprint of the JVM. They've been doing that with the heap space already. Another thing they've improved is the ZGC collector. So they've gone for the idea of concurrent thread stack processing. This is to do with how they create their root set when they're starting to do the processing of the garbage collection. So they've removed all the thread stack processing from within the safe points. So this is where they kind of get all the threads to a safe point, and then they're able to do certain things. They've moved that work out of the safe points, so you get shorter pauses associated with the garbage collection there. Various other things. So they made the stack processing lazy, cooperative, concurrent, and incremental. All sounds good. And they've also removed all the other per thread root processing. So that's the root set again from the ZGC safe points. Nice thing about this is that the code that they've done for this, they've actually made or designed it in such a way that it can be reused by other garbage collection systems. And I saw a thing on one of the threads just last week. They were talking about how Shenandoah is making use of this so they can improve the efficiency of that algorithm. Strongly encapsulating JDK internals by default. So this is this was introduced in JDK 9 and essentially was part of the modularity. What they wanted to do was take all the internal APIs in JDK and just turn off access completely. That wasn't a good idea because it was going to break too many applications and frameworks, things like Spring and so on. And so they introduced this wonderfully named big kill switch, illegal access. So that had 4 options: permit, warn, debug, and deny. And up until now, the default has been to permit, meaning you still have access to the non-critical internal APIs of the JDK. What they've done in JDK 16 is turn that to deny, meaning you no longer have default access to the non-critical internal APIs. The important thing is that the critical internal APIs are still not encapsulated. So that includes SunMISC unsafe. If you're using those in your applications, which you shouldn't be, then you still have access to that. The idea is to replace the functionality of SunMISC unsafe at some point in the future. Things like the foreign memory access API is part of that. There's still some other work going on. Packaging tool. This was something that was in the JDK, was at least in the Oracle JDK as part of JavaFX. When Oracle did some cleaning up with JDK 11 and eliminating differences between the Oracle JDK and OpenJDK, this got removed, and people said, "Oh, we like the incubator, we like the Java packager tool, make it an incubator tool," and so that's what they've done. Now, it's a final feature in JDK 16. What it allows you to do is create platform-specific packages with all the necessary dependencies. So if you're running on Windows, you can get an exe file, MSI file. Linux, you can generate RPM and deb files, macOS, package, and DMG files. And it builds on top of JLink to generate the tailored runtime that gets included in your package. So everything's in there, and just deploy it where you need it. Just to summarize, basically, as I said, the 6-month release cycle seems to be working really well. We've seen lots of new things added to Java, far more than we've ever seen in the past, far more quickly than we've seen in the past. JDK 16 has got some interesting things in it. I think the vector API is quite interesting. The work around replacing JNI through the foreign memory and the foreign function APIs is all quite interesting. And seeing some of the preview features being moved into final features is very reassuring as well. So pattern matching of instance of and records is really good. And I'll just say, use Zulu builds of OpenJDK if you want to deploy to production. Just very briefly mention Zulu Enterprise. This is our build of OpenJDK. It's available for free, so you can get that from our website. We support all the way back to JDK 6, although that's yes, all the way back to JDK 6, fully TCK tested. We've also backported things like TLS 1.3 and Flight Recorder to JDK 8 from JDK 11. Lots of different platforms supported, Intel 64-bit Windows, Mac and Linux. Even if you're using Windows XP, we have Windows 32-bit versions and Linux 32-bit versions as well, and it is very much just a drop-in replacement for the Oracle JDK. And so with that, questions?
Yes, thank you very much, Simon. That was, well, actually amazing to learn how Java keeps getting better and better. So we again have a few questions. One again about records.
Okay.
So would records work with Lombok Builder instead of a constructor?
I'm going to say I don't know the answer to that because I don't know Lombok. So I would not want to hazard a guess at that.
So if anyone in the chat wants to answer this question, go ahead. Another one about Unix domain channels. Is there a fallback for Unix domain socket channels or for any OS that doesn't support Unix domains channels?
No, I don't believe so. I'd have to check it, but I'm pretty sure that what you get is just a unsupported, whatever it is, exception.
Okay.
Yeah, so if you try and run it on a platform that doesn't have that, but even Windows has Unix sockets now, so I think you'd struggle to find a platform that didn't support it.
Yeah, makes sense. About map multi, could you use a filter after map multi instead of an if condition within map multi?
Yes, you could, but the whole idea is that it's a way of combining things. So yes, you could definitely use a filter. What most of map multi does is not anything radically new. It's just replacing like sort of 2 lines of code with 1 line of code type thing.
Yeah. All right. So so one of the reasons we asked you on stage tonight is because OpenValue and Azul are having a great partnership, working together. And you already mentioned a little bit about Zulu, and well, you explained quite well, I think, what you're offering there. And I think it's also nice maybe to explain a little bit about Sing. It's a really interesting JVM. Can you explain a bit what Sing is?
Yes. So Zing is where we try to look at how the JVM performs. And the JVM is very good. It's obviously developed hugely from when you look back at JDK 1.0. You know, JDK 1.0 had very primitive garbage collection. It didn't have any form of JIT compilation, so it was very slow compared to natively compiled code. Now, we've obviously gone through lots of iterations, and we have things like G1 as a garbage collector. We have, you know, C1, C2 as JITs, all very good. But what we've done is look at that and say, how can we improve that even further? And the thing that we did initially was to look at improving GC and eliminating garbage collection pauses. So we took all the garbage collectors out of HotSpot and replaced them with one that is called C4, the Continuous Concurrent Compacting Collector. So it does all of the garbage collection concurrently, so you don't have any stop the world pauses for your garbage collector. Obviously, we're seeing things like Shenandoah and ZGC more recently that do similar things. Both of them do still have stop the world pauses, even though they're short, but they do have stop the world pauses. C4 does not. Then what we've done more recently is looking at how to improve not just the latency of the JVM and how it delivers to applications, but also the throughput that you can get. And what we've done is replace the C2 JIT compiler with one that's based, as I said, on LLVM. It's an open source project. And that's a project which is designed to essentially be the back end of a compiler for a static compiler. So it takes intermediate representation, heavily optimizes it, and generates native code. So we integrated that into the JVM as a JIT. We contributed it back to the open source project, the changes that we made. And now what we're doing is using that so that we can get more heavy optimization of the code that's generated by the second JIT. And that does include a lot of vector operations. And again, as I said, we will recognize a lot more things that can be used with vector operations. We're also doing a lot of interesting things around escape analysis and better intrinsics and various things like that, so that you don't have to use these sort of APIs to try and give hints to the compiler. We can just recognize code more easily and optimize it so that we get better performance out of the code that's generated. So that's kind of what Sing is all about. It's better performance for the JVM.
Really some impressive feat of engineering you guys did there. Mm-hmm. So there's one last question, a nice one to end with, I think.
Okay.
What's your favorite new upcoming feature and why?
I've got to say I like records. I think records is my favorite feature at the moment. Although I will say that I think JDK 14, yeah, my favorite new feature in JDK 14 was the helpful null pointer exception. Just how it's taken 25 years to get to the point where we can actually see, yeah, if I do a.b.c.I and I get a null pointer exception, where was the null? Was it A, was it B, was it C? You know, having that I just find really, really useful, because you find it surprising, but occasionally I get a null pointer exception. But yes, records is the other thing that I really like, because it's one of those things, and I've discussed this with Brian Gertz in the past as well, is like why we don't have a tuple in Java, and there's good reasons why, you know, it hasn't been there before, but just being able to create records and simplify the whole idea of simple data types, I think is very, very powerful and makes code really nice and, you know, compact.
All right. So thank you again for sharing your passion and enthusiasm about Java. It was a really great talk. We will have now a short break in a moment, and we will then continue with the grand finale. We will have a compiler pub quiz. So stay in the meetup if you want to win a very cool prize. In a moment, there will be a sheet up showing a link you can visit. Go to the site, accept the license and choose a nickname. Then you will be all set for the pub quiz. It will start after the break. And we will be back at in 8 minutes, 2010. So see you back in a couple of minutes. Thanks. Hi, welcome back, everybody. So I hope you enjoyed the first talk and the short break. So now for a little bit of relaxation, let's get going with compiler optimizations. Always fun, right? Well, maybe. Because Jago created a really nice pub quiz for us, as promised. And the good news is that Jago knows where he's talking about. He already shared lots of his Java-related knowledge on multiple conferences in different countries, including conferences like JVOL, DevOps in Belgium, JavaOne, and also QCon. And he's also a very experienced developer, and with his quiz today, you can win a special prize. You can win a free talk or a workshop from OpenValue. So this can be provided for your team at a company meetup, or maybe you want to have a private talk. So that will be possible. You decide. The second prize is also very special. It's a full year of AWS free tier usage, sponsored by our partner Amazon. So now let's get started. First, a question to Jaco. Why did you pick such a kind of boring subject as compiler optimizations in the first place for a pop quiz?
Yeah, that's a good question, right? Actually, a lot of my job is figuring out where bottlenecks are in pieces of code. So optimizing small chunks, usually they are a mess anyway, so that's easy to optimize. But once you have some clean code, well-written code, it's really hard to define where the problems are. So you need to dive in a little bit deeper into the ecosystem to figure out where the problems are. So compile optimizations are a way of fixing most of those problems, but you need to know where to look and well, how to uh, uh, how to use them. So normally these talks are heavily based on bytecode and even machine code and really dive in deeply. But that's not what I really wanted. I wanted to show some real use cases that well you could pick up today and maybe implement tomorrow in your code and write cleaner code or better code or at least better performant code, or make the decision of why you choose something A over B.
That's all right, cool. Really curious to learn about the quiz. So I see that now currently 24 users are connected. You can use the link in the chat to visit the site or scan a QR code with your phone. And now, please give the word to you, Jaco. Take it away.
Yeah, thank you, Roy. So, welcome to the introduction. Like I said, this will be a high-level introduction of how the Java hotspot compiler works. And you might think the hotspot compilers, hotspot JDK, well, there's just only one, right? Wrong. The hotspot compiler is implemented in most JDKs. Not all of them, but at least the most used ones and the big ones have a hotspot compiler in them. For example, the Oracle JDK, because that's the hotspot JDK, but also Graal or Azure or Amazon has a JDK. So all those JDKs have a hotspot compiler in them to optimize the code that you're using. So this will be a high level and with some questions. Please visit myquiz.org and log in. The QR code will remain on the screen for a few slides. And then we dive into the questions. Please bear with me. I'm single-threaded, and I need to do a lot of context switching because YouTube is lagging behind around 7 to 10 seconds. So I need to synchronize while speaking and reading the questions. And that's also why I will be actually explaining the answers and then showing the results of the questions, because normally you want to see how everybody did and then comment on that. But when I'm discussing the answers, you guys will still be answering the questions. So that's really a struggle for me. So please bear with me. So normally we write code like this. Right? This is a simple string statics class with a string hello world, and well, it's quite easily. So what you've written will be compiled into bytecode. So for example, this method will result in something like this. This is the bytecode that is used by Java to run on every system. So this bytecode is machine agnostic. So any machine that runs Java can normally run this code. So what the Java runtime needs to do is interpret this bytecode into machine code. So this bytecode will look like something like this in machine code. And I promise this will be the last slide of machine code or bytecode. So what you see in machine code is a lot of jumping around, comparing stuff and moving all kind of stuff through registries. This is the code that the hotspot compiler will actually optimize. So not going to dive into this because that will be boring. So a little bit of background. There is something called a tiered compilation. Maybe you've seen that. But the first tier is tier 0, and that's what most of the applications will run in, because that's the interpreter mode. That's the mode when the application has just started up and, well, just interprets your bytecode into machine code, and, well, that's about it. But when your code is running, it will go to a number of phases. It will first enter the first JIT, and the first JIT is also called the client compiler. Maybe you have seen those in the past, that your application would start up with an argument called -- client, which signals the runtime that it would only use the client's hotspot compiler, because your code is running shortly. So there's no need to do big performance profiling and add a lot of counters to a lot of code, because those code will run only once or twice and then it's done. But the second JIT, or tier 4, is actually the server compiler. The server compiler will optimize code that's running a long time, or at least is called a lot of times. So around a few thousand times, it will start to optimize your code. It can only do that when it knows it has run a few thousand times. So it needs some counters and profiling data. And that counters and profiling data is actually provided by the first JIT. But when your application is starting up, then you will see that the second JIT, or the server compiler, is actually quite busy, because a lot of code is spun up, a lot of code is executed, and all is fed to the second JIT. It's still figuring out what to optimize and what not. So when it's too busy, the first JIT will only add counters. So it won't envelop in everything to create a lot of profiling over a lot of code that will slow your application down. So it will only add simple counters for your piece of code. And based on that, it can make some decisions to either optimize it or not. And when the second JIT is actually a little bit freed up, it will actually start entering the profiling stage and adding profiling, and add it later to the server compiler. But there's also something called a trivial method, when the method is so simple that the client JIT can optimize it. It will actually handle it itself, and then it's done for. So that's the JIT compilation. And the question will actually sometimes go about the interpreter and the second JIT. So what are the difference in performance between the interpreter mode and the second JIT? So I'll leave out the small optimization that's done in the first JIT and focus on the second JIT, although some of the optimizations are done in the first JIT, but those optimizations are still valid in the second JIT. So how does this look like when your application is running? Well, if we graph it out over a number of iterations, first your code will run quite slowly in the interpreter mode, and then the first JIT will kick in, do some optimization, do some estimations, maybe optimize it wrong, do a lot of stuff, add a lot of profiling data, and then the second JIT will actually dramatically improve the performance of your pieces of code, and then it will run a lot faster. Although sometimes the second JIT makes a wrongful assertion. For example, that a field is always A or always B, and then it encounters that field will also be C. Well, you didn't expect that one. So it needs to de-optimize the piece of code, and then it will repeat back to the interpreter mode and actually the first JIT. But then it knows what it can expect. So the next iteration of the optimization will be a lot smarter and a lot better. it might not run as fast because it now needs to handle more branches, for example, but hey, at least it's running constantly. So doing performance testing in Java is quite annoying because you need to have reliable results. And for that, I've used the JMH. That's the Java benchmark harness, and that's really useful for benchmarking small pieces of code. So when we dive into an example of this, you'll see a piece of code with a lot of annotations. Well, it's just plumbing. You can, for example, say how much warm-up iterations it needs to do, how many iterations it actually needs to do the measurements, create some data, do some setting up. But actually, the most important part is in the box, and that's the benchmark method. For this case, it's a forward loop, and it always, or usually takes a black hole with it, and that black hole is used to actually consume stuff. Because the hotspot compiler is quite frank to optimize a lot of code. So if we do not use the black hole and have a loop that iterates over a big array, for example, and only does the get of a element and assign that to a string and does nothing with it, the hotspot compiler will actually see that and will see that string s is no longer used. The get is pointless, it has no side effects, so that can be removed as well. Then it will see it has an empty for loop. An empty for loop is completely pointless, so it can remove that as well. And then we are left with an empty method. Benchmarking an empty method is, of course, quite pointless. So that's why we need to have a black hole that consumes, and that consumes something, and actually under the hood it does nothing with the thing that it consumes. But at least the hotspot compiler does not see that, and well, it thinks it's actually does something with string s, and therefore leaves the code alone because it's actually being used. So this is your last time to visit the myquiz.org website and enter the code. I see that there are 25 people are actually in the quiz, so that's a nice group of people. So let's get started with the first question. And the first question involves an array of a class called strings, and it has a final integer number. And what is the most efficient way to do the concatenation of strings? Will A be efficient, or should you stringify the integer into a string of 10, or just make it easy for the compiler and do string 10 times in one string, so it doesn't need to figure it out? Well, actually, all of these answers will result in the same bytecode. The fun thing is that the hotspot compiler will automatically optimize and concat any strings. So what it does is the string of the integer number, it can, as it is final, it can encapsulate it into a string. So it does that on compile time. Then it's the same as B, but B is only adding 3 strings to a single string. Those 3 strings will never change after they've been compiled. So what the compiler actually does at compile time is create one string called do 10 times, and that's about it. So what I've heard in the past was that a piece of code was called many times, and somebody split up a string into multiple lines because it was better readable. Then somebody said, well, that's not really a good idea because the performance of that is worse. But as you can see, the performance doesn't matter because it will actually be that one string after it's been compiled. So it's completely pointless to have a big string 8,000 characters in. Just split it up into multiple lines and the compiler will handle this for you. And luckily, 28% of you guys also knew that, so that's kind of cool. So the second question. The second question will be first a greet string, which does not have a final, and B has a final. Which one will be faster? Well, this should be easy. Well, actually what happens here is quite funny, because what you can see in A, the piece of code that does not have a final in it will create at compile time a string builder. The string builder is used by the Java compiler to concat any strings. So that's normally that it will use that. But the compiler will clearly see that the greet variable was only used in the line below, never changed. So why didn't it optimize it? Well, a variable is a variable, and that can change according to the compiler. So that's not something the compiler will see. So A will actually create a new string builder, and B, as it is final, can be inlined into the string, and well, that will be just one string. So that's a lot faster. So what I've tried to do in every answer is write down the interpreter time and the time that it took the second JIT. So as you can see, option A is around, well, almost more than 10 times slower than option B. So that's really good to know.
There's a question, Jago, from Nick. Is effectively final. Isn't that the same?
It's almost the same, but it's as you can see, the compiler will not see that, and it will not optimize it the same way as it is a real final. So it should see it, but it doesn't see it, and it's still the case in JDK 15 because that's the last JDK that I've tested this on. So, well, it's still in there, and well, it could be improved. So next question, a string concat loop. Well, this is fun because I've seen this quite often in the real world. Whereas A is a string that's just a string that's concatenated into multiple iterations, or B, using a nice string builder and using that for a way to concat the result into a string. So I see that there is some slight thingy wrong with the quiz. It requested A, B, C, and D, while there was only A and B. And it said D was the correct answer, so that's my bad. But luckily nobody guessed that right, so everybody gets the same number of non-points. But the correct answer would be B, and luckily 54% of you guys did see that.
So, there are a couple of questions coming in, also about the last question. So the final thing, is it only true for strings? Is effective what you told us?
It's not only true for strings, it's true for any variable that you decline. So if you created a variable integer or int, it will not inline that until it's final.
All right. And do you know how well other JVM languages like Kotlin exploit this?
I have no clue. So if anybody knows that, leave it down in the chat or leave it down in the comments.
Thanks.
So the string concat loop, well, as you can see, what happens in bytecode is that option A will create a string builder to concat the integer I to the result. So for every iteration, it will create a new string builder. And well, creating a new string builder is quite, well, not quite expensive, but it's a little bit expensive because the garbage collector also needs to clear that thing up. Whilst option B, well, you have one string builder, and that one string builder is used throughout the loop, and no new classes have been created. So luckily, most of you guys knew that. Unfortunately, something went wrong with the quiz here, so hopefully I see what went wrong. It showed the wrong question, because the question was about inlining. So let me give first an introduction into inlining. Inlining is when a method calls another method, and that method is called so many times that the compiler will see, hey, why not inline or include that piece of code that's in that method into the method that it's calling. That would optimize it a little bit, because it will then no longer need to do a method call. And as it's no longer doing a method call, it's a lot faster because it doesn't need to do any stack manipulation and that kind of stuff. So inlining is quite fun. So the question would be, how far can we take this? But that's the question that we already done. So that's really annoying. So this is the annoying bit of doing a live quiz and seeing what's going on. I guess somehow a question got removed from the quiz. I'm sorry about that, but I will give the answer to this one. The inlining, actually, you can take inlining quite far, because in option C, you will see that it creates a new calculator class and then call the method sum on that. What actually the hotspot compiler will see is that the new calculator class is being created and then no longer is used, but also it doesn't have any side effects. It only is used there to function as a method wrapper or helper class for the sum method. It will actually remove out the entire instantiation of the new calculator. That way, it's just a method called sum, and that way you can inline the sum method. You can even take this a little bit further and have a real sum in that question, and that will also be inlined, because that's just one nesting further. There is a limit to this, however. You can only inline 9 methods, so that's really not that much. If you're really going berserk in clean coding and use a lot of small methods, you probably will hit the limit of which methods can be inlined and which will not be inlined. Luckily, there's a compiler flag for that, and that's called max inline level, and you can set that, and that way the compiler knows what you actually want to do, and you can set it, for example, to 36 or so. Because that 9 was chosen, I believe, in JDK 1.3 or 1.2, at least a long time ago, when this optimization was introduced, and never changed after that, because, well, it would probably break backwards compatibility if somehow it does 8 or somehow does 20 inlining attempts. So you can tune this. Well, it's quite fun to tune around with this one if you're using a lot of small methods and using extreme clean coding. So, next question, and actually the question that's in the quiz right now. So you have a lot of time to read the question in the quiz. And that's about a to-array. Which is faster, string 0 or creating array with the size of the actual list? So what you will see is that the string 0 is a lot faster than with the size. Well, it's really odd. And the fun fact is that even Finebugs used to incline that it was faster to do the size method instead of the 0 one. So what's going on here? So if we go and look into the toArray function, that's actually using an array copy function underneath. It will see if the destination size, if it's 0 sized, it will do just a simple malloc function call. It will just allocate the memory that is necessary for the array, and then it's done with it. But when you pass it in an array that already has a size, it does not know what to do with it. It could be an array that's also already being used or not. It doesn't know that. So what it does is actually iterate over the entire array and will null out the entire array. So it needs to iterate over the entire thing. So that's a lot slower than just a malloc call and allocate some piece of memory that's probably available. So this is why giving it the size 0 is faster than the actual size of the array. So next question, that's about boxing. In this case, we have for A, the primitive version, or B, the box version. Is the compiler able to actually optimize this piece of code? Can B be as fast as A when it's optimized? The answer is option A is a lot faster because it does not need to do any out-of-boxing. The compiler will not see that it's only being used for calculation and just that's a wrapper object. It will just leave it out as an integer class and will actually be boxed, and that boxing is pointless and takes a lot of time, around 10 nanoseconds per operation in this case. So that's quite big of overhead. So if you're doing calculations with integers or any primitive types, please do them with primitive types and not with the object type, because, well, as you can see, it's quite slow compared to the original one. So null checks. I heard a lot of times null check hurt performance. Don't use null pointers because blah blah blah. So that's is that the case? Is option A as fast as option B, or will B be faster than A with a null check? So this is something well, you see a lot of times in code. And well, I actually saw that the question was not started at the correct time, but hey, you can't win them all. What you can actually see, what is happening underneath, is that when the second JIT kicks in, that you will see that the performance is around the same. In interpreter mode, the null check is a little bit slower. Well, that's what we can assume, because a null check, well, it does something, it's code, it needs to be executed, it needs to check something, so that needs to take a little time. So option B is, of course, faster in interpreter mode. But when the hotspot compiler gets a hold of it and actually optimize it in the second JIT, it will actually completely remove the null check if it's never encountered any nulls. That's the big caveat here. If the null check sometimes encounters a 0 and sometimes a non-zero or non-nil, then the check is valid and then the check needs to be executed every time. But if the check always ends up in the same state, that holds true for any Boolean check. So if the Boolean check always is the same, then it will be completely removed. And that also includes every piece of code and every thing with it. But you might say, but what will happen if string s becomes a null all of a sudden? Well, then it actually will run into a null pointer exception. And underneath that will be a segmentation fault at runtime. But Java will catch that segmentation fault and will see, hey, a null pointer is not something I expect here. My assumption that I removed a check for null was invalid. And then it will de-optimize your piece of code, and then we'll add in back the null check, and then we'll know, hey, the null check is valid, and well, it needs to be actually be there because sometimes it is null and sometimes it's not null. So what you can see actually in the machine code that's being generated, well, the first piece of code has a little bit more bytes of machine code than the second piece, because, well, it's in the second piece it's missing out the null check. But when it's fully optimized, it's exactly the same number of bytes. Well, that's really cool. So next question, let's make it a simple one. And that's about math. If you do a lot of math, which one is faster? Java 8 or Java 9? And I know there is a fast math library in Java 8. So we're comparing here the stock math libraries from Java 8 to Java 9. Well, luckily, of course, Java 9 is a lot faster than Java 8 because they swapped around the math library under the hood. So that's why Java 9 is a lot faster. And as you can see, luckily, a lot of you guys knew that already. So that's cool. So for loops, which one is more efficient? The classic int for the classic loop, or a while loop? It's a bit of battle of the old for loops. I don't know who uses them on a regular basis. Well, you should use them if you want to index for something, but there are modern ways to do this. And fun thing is that is actually the same piece of code that you're looking at. B is the compiled version of A. A is nothing more than compiler or syntactic sugar. And I see that, well, almost everybody knew that, so that's kind of cool. So next way to write for loops. That's with a enhanced for loop, or use a iterator. But also here, it's exactly the same what we're looking at. Option B is the compiled version of option A. Option A is nothing more than syntactic sugar again. It just uses the iterator to iterate over your list, for example. And, well, this surprises me a little bit, but because it's called the advanced for loop, so well, it's only syntactic sugar. So, well, this is something to keep in mind. So an enhanced for loop is not faster than an iterator because it's an iterator. So pitting those two together, the advanced for loop versus the old one in A. So option A is the old one, and option B is the enhanced for loop or the iterator. And option A is of course the same as a while loop. And this one yields a very interesting result. This is a result that I find quite interesting, because what you will actually see is that with B, that's a iterator, it will create actually a class, because you will get a iterator, and, well, that's a class and needs to clean that one up. But when it's iterating, it's well, a little bit faster. When it's fully optimized, well, then there is no point of using or choosing either of them because they will compile out to roughly the same piece of code. So that's not what you want to optimize for. But when you have a lot of code that's running in interpreter mode, a enhanced for loop is faster than a old for loop.
So there's a question slash remark, Jago.
Yeah.
Is it not based on the implementation of list?
For this question for B.
I guess, yeah.
Good question. I'm using a array list here. But I think it's of course the iteration speed of any type of list will differ. So I might forgot to tell this is a array list. Because of course you have a linked list and a lot of other types of lists, and those perform in different ways. So these results are valid for array lists. So good question, good remark. So what's going on in a array list then? What you will see is the list.size is actually called for every iteration. So, and it will actually do some nasty checks underneath as well, because if you look at the code that's being used, the size will actually check for code modification and that kind of stuff. So it needs to do a lot of kind of checks, and that way it will slow down a little bit. You could try to assign list.size to a variable, but somehow it won't be optimized as it would normally be. And that's probably because the optimization that are done are quite strict in what kind of syntax they expect. So if you move some pieces of code a little bit, then it won't be optimized at all. And I think that's the matter here, because it won't recognize it as a normal for loop. It won't do, for example, loop unrolling, which I don't go into here at this time. But this is the way the normal for loop works. And you'll see a lot of method calls in there. And with the iterator, it is almost encapsulated into a single method. So there's no overhead in calling a lot of other methods to do manipulation of the array and that kind of stuff. And therefore, it's a little bit faster. And especially with big arrays, this holds true. For small arrays, the speed change is not that dramatic. So, and especially when fully optimized, it's gone as well. So please use whatever you feel inclined to. But there is another way to do loops, and that's the cool old new way of lambdas. So which lambda will be faster, or option C, actually use the old style of iteration. And option B is actually the method reference that we use. It's the same, or it calls the same method as option A. So this one is funny as well, because what you will see here is that the lambda is actually faster than the old style of iteration. That's kind of weird, isn't it? Well, it's not, because the for each function, or the for each lambda, is actually running inside of the array implementation and doesn't do any other method calls. So that way it can eliminate a lot of checks, a lot of concurrent checks, and ensure that it's running as fastly as possible. And option B, a method reference, it's faster when there are a lot of items in your list, but if there are a few, it doesn't really matter. And that's because a method reference should be assigned to a variable first and then used, but the compiler will optimize that out for you, so you don't have to write that piece of boilerplating. Actually, you can't really write that piece of boilerplating, but it's something that the compiler will do for you. So that's why for small lists, that's a little bit slower because, well, it needs to create that method reference first and then use it. Whereas the other lambda, well, it's just created once and then actually being used a lot of times. So lambdas with a for each loop in our array list are really quite fast. So that's quite cool. And again, luckily, I see that a lot of people already knew this, so that's cool. So to wrap it up, and actually go to the leaderboard, we see that DT has won this competition, and it was quite fast as well, in 2 minutes and 50 seconds. So Yogi was a little bit faster, but had some questions, or had less questions, right? So congratulations to DT. You can contact Roy and claim your prize. Details should be in your screen right now. So to wrap it up with a nice quote of Kurt Donald, we should forget about the small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass the opportunities in that critical 3%. So taking that a little bit liberally, is to say write clean code first and only optimize your code if you determine that there is a significant problem with your specific piece of code. So don't try to implement all kind of optimizations at first. Probably it won't have any effect at all. So are there any questions, Roy?
Well, we handled a couple of questions during the quiz, of course. I don't see any questions at the moment. I must say I kind of made fun of the subject, saying it was boring and stuff, but it was absolutely tons of fun. I mean, loads of gotchas and some really surprising answers. So yeah, a really great quiz, Jago, and well. Like you said, DT, you can write me an email or contact me otherwise on Twitter or whatever. Roy@openvalue.nl is my email address, and we can talk about how to get you your prize. So if there are no questions, no, I don't think so. Then we're gonna conclude this meetup. I hoped we would finish before 9 and we managed, so well done with the timing as well. Thank you all very much. It was I think our best attended meetup as well, next to being the best subscribed meetup, so that was great. And we hope to see you at our next meetup, which will be in February. And of course, don't forget to like and subscribe our YouTube channel if you liked all this. And that's it for us tonight, and enjoy the rest of your evening. Thank you very much. Bye.
Bye.